Got another exam question for you from Thermodynamics 2021 October. This is going to be another exam walkthrough in thermodynamics physics. So I've got a really good question for you. It says a kettle was used to heat 855 grams of water to boiling point. The initial temperature of the water was 21.5 degrees Celsius and it took 115 seconds to heat the water to 100 degrees Celsius. The kettle is left switched on for 175 seconds after the water has. Okay, so the question says to us, we have 855 grams of 855 grams of water in a kettle, and the temperature increases from 21.5 degrees Celsius to 100 degrees Celsius. And this happens in 115 seconds. So in 115 seconds, the temperature increases. So the kettle is supplying energy to increase the temperature. After that, what happens is that the temperature remains constant, but the mass of the water changes because some of the water is going to evaporate. The kettle is still supplying energy, but that energy is going into changing the state of water from water to gas state. Okay, so we have to find how much mass basically would have converted into steam and boiled away. Okay, that's what we have to calculate. So first of all, what I can do is I can find the energy in 115 seconds that was gained by the water. So the energy that the water gains is the energy supplied by the kettle. So I can find that out by E is equals to mc change in temperature. And that gives me a total energy of this much. Okay, that's 2.812 times 10 to the power 5 joules. Now, this much energy I get in 115 seconds. So I can just find the power, which is equals to energy divided by time. And I get the power as 2445 watts. And now I can find the total power in 190 seconds, and that's power times the time. So now I can find the total energy in 290 seconds, and that's this much energy is the total energy given. Out of this much energy, out of the total energy, some of the energy goes into increasing temperature and the rest of the energy is gone into vaporizing. So we know how much energy goes into increasing temperature because we already found that out. That was this much. And now we also know the total energy in 290 seconds. How do I know it's 290 seconds? Just add these two time values, you'll get 290 seconds. Okay, so now what I can do is I can find the energy from vaporization, which I can just move this to the other side. So I can get this as the energy needed to vaporize water. And this energy needed to vaporize water or change water's state is equals to m times L, where m is the mass of the water that has changed its state. So then I can just use the value of the latent vaporization, specific latent heat of vaporization, which is given to me above there. And I can divide it by the other side to get 0.198 kg, which I can times by 1000 and get 189 grams. And that's my answer. Okay, you can do it. You can actually skip some of these steps. You can just multiply this actually by 175 as well and just do it straight up. But I just wanted to show you this part specifically, that our energy is split into two things. One, increasing temperature, and the second one is changing state. Okay, so this is the entire working for 4 marks. Okay, another one is a simple question. Natural gas produced from landfill consists of a mixture of methane and carbon dioxide gases. At a temperature of 20 degrees Celsius and a pressure of 1.01 times 10 to the power 5 Pascal, the volume occupied by 1 mole of carbon dioxide is 0.0421 meter cube, so that the number of molecules in 1 mole of carbon dioxide is that much. Okay, so we can solve it and I'll show you the answer. So first, we know the equation PV is equals to NKT, where N is the number of molecules. Okay, and now what I can do is I can just plug in the values of the pressure, the volume, the temperature, plus 273 always, because we want to take it in Kelvin, and then the value of K, the Boltzmann constant, and we'll get an answer of 6.019 times 10 to the power of 23, which is approximately equals to 6.0 times 10 to the power of 23. Pretty simple, pretty straightforward. Okay, the next one is a little tricky. Give me a second. So the next part says, a sample of natural gas, the root mean square velocity of carbon dioxide molecules is 60.5% of the root mean square velocity of methane molecules. So then they give you the formula for the root mean square velocity, and they tell you to find the ratio between the mass of carbon dioxide and the mass of methane molecule. So you can try it yourself and then I'll tell you the answer. First of all, you should know the formula of average velocity. The average, kinetic energy. The average kinetic energy is equals to half m, the mean square velocity. I can make mass the subject and get this as my formula. Okay. So then I can say that this is the kinetic energy of carbon dioxide. I'm representing it with C here. The mass of carbon dioxide and the mean square velocity of carbon dioxide. The kinetic energy of methane, half, mass of methane, the mean square velocity of methane. Then what I can do is I can say that I can divide both the equations. Okay. And if I divide both the equations, my 2 will cancel out, half will cancel out. Okay. Let me actually, because this I've done a little differently, I'll do it like this, okay? We will divide both the equations. So once we divide both the equations, we'll get KEC divided by KEM is equals to MC and then MC square M, okay? So this here is the kinetic energy of carbon dioxide, average kinetic energy of methane, mass of carbon dioxide, mass of methane, the mean square velocity of carbon dioxide and mean square velocity of methane. So what we want to find out in the question is the ratio between mass of carbon dioxide and mass of methane, right? And we have in that form. Okay, so I can take this now, both of these, and move them to the other side. Okay, and that would give me KEC, and then this, and I can divide it. Square C. Okay, so this is what I'm getting now. Now, one thing you must be very careful about is the average kinetic energy is same for all of the molecules, no matter what mass they have, what mean square velocity they have, same. But the mass and the mean square velocity will differ. But when you multiply this with and then times it by half, and you're going to find the average kinetic energy. Average kinetic energy for everyone will be same. All the molecules, maybe it's small, maybe it's big, all of them will have same. So essentially what we're going to do is we're going to cancel these out. Okay, so we're going to get the mean square velocity of methane and the mean square velocity of carbon dioxide is equals to the mass of carbon dioxide divided by the mass of methane. Okay. Now, what you should know by now is that the root mean square velocity of carbon dioxide is 60.5% of the root mean square velocity of methane. So I can square both sides and I'll get the mean square velocity of carbon dioxide is 0.366 the mean square velocity of methane. Okay, I just square everything. And then using this, instead of writing this, I can substitute this. Okay, I can substitute this, and when I substitute that into the question, I can see that my methane mean square velocity gets cancelled out, and I get 1 over 0.366, which gives me the answer as 2.732. Now remember, this expression is equals to the mass of carbon dioxide divided by the mass of methane. And I just, instead of writing the mean square velocity of carbon dioxide, I just substituted it with 0.366 mean square velocity of methane, and I got the answer as 2.7, which is the final answer. Okay, I have to explain all of this, but in exam, you should be able to do this very quickly. Well, that's it for this video.